Okay, I think I'm going to get started with introduction. I can kind of slow walk the introduction so we can allow people to come into this room. But I just want to warmly welcome everybody to this Garcon side event called Hydrological Forecasting for Eastern Africa. And as you can see, this is a session that is organized by the Down2Earth project, which is an EU funded project with partners across Europe and Africa, and especially including ICPAC. So it's sort of a natural extension to this Garcon process. Our agenda for today is that we will briefly try to get to know you a little bit more so we understand the audience that we're speaking to. And to do that, we're going to use, and throughout this presentation, we're going to use an online software that you can access through a mobile phone, etc., called Mentee. You can see the website at the bottom of your screen, www.mentee.com. And if you go to that site and then punch in the code that you see at the bottom in yellow, you'll be able to access all the relevant polls and that we have within this presentation, and so that it becomes more interactive. So after we get to know you a bit, I'll give a brief overview of the Down2Earth project and specifically how it's relevant to the side event today. And then I will hand it off to Dave McLeod, who's based at Bristol, University of Bristol, who will talk about the experimental water forecasts and specifically highlighting the results that we've obtained for the upcoming MAM season. And then we'll do some other mentee questions after that to basically get some opinions from people in the audience about their opinion about how these new forecasts might be useful. And then Dave will hopefully do some demonstration of some new data layers that we've created for the East Africa Hazards Watch desktop app, which is hosted at ICPAC. Unfortunately, we learned this morning that there was a power cut where the servers are located, and currently that website is down, which means the desktop app is also down. We have taken some screenshots that we plan to use to introduce the new data layers, and but we're hoping that maybe the app will come live again before we get to that point in the presentation. And then we'll have a wrap up and some feedback and discussion and allow people to ask any questions they might have about what we've done here. So I'm Michael Singer. I'm based at Cardiff University, and I'm the PI on the Down2Earth project. The other people involved in the front end of today's side event are Dave McLeod, based at University of Bristol, and Jake Rigby, also based at University of Bristol. So I guess you can go ahead and connect to the Mentee at this point, and then we'll move on to the next section in the presentation here. And really, this is about trying to get to know you a bit more. And so the first question is, what is your main sector of focus? And this just kind of helps us gear our presentation toward the appropriate audience. I can see most people so far seem to be focused on water and energy. We have some others on climate change, some research academia, conflict, early warning. But we'll feel free to take some time to punch in some results so we can get a sense of who you are. But yes, one thing I will say now, and we'll say it again later as well, is that we would really like to engage more with this audience and an expanded version of this audience to get feedback on what we're doing here and to better understand how we can together improve the products that we're generating to maximize their uptake and use within the appropriate sector of interest. So yeah, we're getting a lot of population here in water and energy, research and academia, a few others in disaster risk management, climate change, and conflict and early warning. Okay, that's good. It's good to know that. I guess we're safe to move on to the next question. So pretty straightforward, but we want to get a sense of the geographical regions of focus for your work so that we can absorb more carefully what people's concerns might be. Okay, we can see some Ethiopia, Kenya, the whole Greater Horn of Africa region, the IGAD region, Somaliland, Somalia. And someone says other. So I guess the really good news here is that the Down2Earth project is mostly focused on the Horn of Africa drylands within Somalia, Somaliland, Kenya, and Ethiopia. So, you know, hopefully this will be of broad interest to many of you. But the kind of the products that we're generating should be more broadly applicable across the IGAD region and the Greater Horn of Africa. Okay, thanks, Dave. Next. Okay, so what I'm going to do now is give you an introduction to the Down2Earth project and specifically about how we got to where we are today. So the Down2Earth project is, as I mentioned, funded by the EU Horizon 2020 program. And it's really this nice collaboration between European institutions and African institutions. Many academic institutions, but also climate services organizations, media organizations, charities, think tanks, etc. So quite a wide range of partners involved here. And it's really an interdisciplinary study that's trying to translate climate information into multi-level decision support for social adaptation, policy development, and resilience to water scarcity in the Horn of Africa drylands. Next slide, please. So the project is really premised on the point that in some places in the world, that water scarcity also causes food insecurity. And this is in places where subsistence agriculture and pastoralism are practiced, and where people have to travel distances to get access to drinking water. So you can see examples here where people have to travel to a nearby well to get access to obtain their water for human use and livestock, where rain-fed agriculture is the dominant agricultural method, and where pastoralism means that people are moving herds around, moving livestock around to different areas to find appropriate access to fodder, crops, and water. Next slide, please. Now, unfortunately, what we've seen in recent decades is an increasing concern of drought or failed rains within critical rainy seasons that affect these livelihoods I just was talking about. For example, in the last several decades, there's been an increased frequency of very severe droughts with very short-lived periods of recovery. And what happens in moments like that is that people who are living in subsistence communities like this are, on the move, where livestock are dying, where crops fail to grow, and where water becomes a very scarce resource and wells dry up. And that has pushed many people within the broader region of East Africa into severe food insecurity, or even in famine in some cases. Next slide, please. So our geographical focus in this project, as I mentioned earlier, is really in Somalia, Somaliland, Ethiopia, and Kenya, and specifically in the dryland environments within those countries. But we feel that what we're doing here is much more broadly applicable across the Horn of Africa region. The current approach to this problem of drought and water and food insecurity is to look at forecasting these aspects based chiefly on climate information from the atmosphere. So using atmospheric variables such as rainfall and temperature to make assessments of what might be happening in terms of impact on the ground. So on the left, you see example from CHIRPS, a rainfall product that is used to convert into a map of projected food security for that same season of interest. Again, entirely based on the meteorological variables. Next slide. But we're very much interested in moving down from the atmosphere down to the land surface and even below it to translate these climate variables into the impact on water access, water availability, water resources, and the associated livelihoods that might support. So we're really after the multifaceted challenges of water scarcity and food insecurity under climate change. And the main novelties of this project are a focus on last mile or rural communities and their perspectives that get incorporated into the co-production of climate services, a new hydrological model for the Horn of Africa drylands that's focused on dryland processes, and we'll talk about that today. Next. A flexible modeling structure that enables lots of simulations that reflect a range of climate forecasts, and conversion of the climate information into direct impacts on water storage and even on crop yields and so forth. And then ultimately incorporation of those new forecasts into both desktop and mobile phone apps. And then making contributions to climate adaptation policies. Can you click the next one, Dave? Sorry, they went in the wrong order. So developing a new agent-based modeling framework led in IVM VU in Amsterdam for simulating emergent behavior that arises from interactions between humans, the environment, and climate-related policies, and using the outputs from that modeling framework to contribute to climate adaptation policies that incorporate the last mile perspectives. Next. And finally, new multimedia approaches to communicating about climate hazards. Next slide. So the modeling that I'll focus on today and that is featured in this site event overall is premised on the idea that dryland regions present different challenges to humid regions. They have a distinct hydrology. Next. So specifically, they have spatially restricted and short-lived rainstorms, really high losses of that incoming precipitation back into the atmosphere through evapotranspiration, very brief and spatially variable runoff events within drainage networks where maybe the channels are dry most of the time, and where groundwater recharge occurs mostly by leaking ephemeral streams in a process we call focused recharge. Now we've developed, oh yeah, stay here. No, stay back, thanks. We've developed a new modeling framework to address these challenges, which has been recently published as an open source software that we call DRIP 1.0. And this is a very simple to use model that partitions the water balance within dryland regions specifically in ways that are not done by current models developed for humid regions. Next slide. Now, the DRIP model was developed at a catchment scale, so for an individual drainage basin, but our bigger aspiration is to scale up to the whole region of interest here that you can see on the right, focusing on the 3 countries focused in our project. And in this case, we're going to embed the drip modeling within a broader modeling framework called QALID, which is, we call it Climate into Useful Water and Land Information in Drylands. And it starts with a top layer of climate variables. So this could be rainfall, evaporative demand within the atmosphere. Those climate variables get filtered through a set of stochastic models that generate individual rainstorms in a randomized way across the landscape and the associated evaporative demand. And once that is done, we get information at a high level of detail about what rainfall is reaching the land surface. And then we conduct the water balance modeling to figure out what happens to it. So some of that water gets infiltrated into the soil, and some of it is lost through evaporation very quickly, or through transpiration, for example, through plants and crops, any kind of land cover. And some of that water may infiltrate below the soil zone and actually recharge the groundwater aquifer through a process we call diffuse recharge. But a lot of it will end up running off the landscape if it's on a slope and organizing itself into streams or channels, stream channels, where it becomes stream flow and where it gets lost, as I mentioned before, through those through those porous ephemeral riverbeds, and then contributes to what we call focused recharge, which again supports the regional groundwater aquifer. Now, this modeling framework is flexible enough to be driven both by seasonal forecasts, which we'll highlight today, but also by future climate change projections. And the idea is that we can generate a whole load of relevant outputs on groundwater, soil moisture storage, crop yields, et cetera, across a broader region. And our aspiration is to have this included explicitly and regularly for the whole region within the East Africa Hazards Watch, a desktop app that is currently rolled out, but starting to develop further, and within a new mobile phone app that targets rural communities and extension workers. Next slide. So the idea is that we would incorporate these forecasts into a decisions workflow as follows. So after the objective forecast is generated through the Garcon process, for example, next, we would generate the relevant water forecasts using the QALID modeling framework. And this is Andres Kichimbo, who's on this call, who's our lead model developer. Next slide. And then that model would generate outputs on soil moisture, groundwater, stream flow, water requirement satisfaction index, and other variables of interest. Next. Those variables could be analyzed by decision makers, and next, and ultimately decisions could be made based on this. So that's the idea that we have here overall. Next slide. And here's just a brief screenshot. Dave's going to show you a lot more, but just to show you, we've already made good strides in incorporating our water forecasts into the East Africa Hazards Watch that allow both an analysis of historical information and information about the upcoming forecasts. Next slide, please. So I'm going to pass on now to Dave to really introduce the forecasting concept, how it was done, and what can be learned from it, and get feedback from all of you. And I just want to say that if you find any of this or some of this interesting, please get in touch with us. We would love to add you to our mailing list. We'll send out a quarterly newsletter to this list and advertise about upcoming events within our project. But we'd also like people to participate within focus groups on this topic in particular. So thanks a lot. And I'm going to pass it on to Dave now.
Thanks, Michael. Great. So, hi everyone. So I'm Dave McLeod, and I'm going to talk to you about forecasts. So, as Michael outlined, our aim is to generate new seasonal water forecasts. And what do we want from those forecasts? Well, there are two two attributes we're aiming for. One is that the output is recognizing the key dryland processes, but we also want them to be consistent with the Garcon forecast. So let's talk about that. So as Michael's outlined, we know in drylands the processes governing water partitioning occur at sub-daily timescales, and in cases even sub-hourly timescales. And research shows that in order to correctly simulate that partitioning of rainfall into soil moisture or stream flow, you need to represent those processes, and you need to have input data to your model, which is at sufficiently high temporal resolution. And that's exactly what we've developed with the drip model, shown on the left, which we've run for a test basin for a pilot application in the Upper Ewaso Nyiro Basin in Kenya, indicated in the map on the right. And we've run historical simulations for this over the past 3 or 4 decades, where gridded sub-daily rainfall data is available. And then on the right, we have the Garcon forecast. So this is the March, April, May forecast for this year, released at this Garcon event. And what this forecast is telling us is providing an indication of the expected risk of above or below normal rainfall. And that's provided as a probability of a tercile where the event is seasonal total rainfall. So these tercile probabilities of seasonal total rainfall are indicated in the plot. In this case, the forecast is going for enhanced risk of above normal or upper tercile rainfall. But we can't use those probabilities of seasonal total rainfall in our model directly. In fact, it's not possible to use those probabilities of seasonal total rainfall in any complex physically based model. So how can we reconcile this? How can we build forecasts which are both are faithful to those key dryland processes, but are also entirely consistent with this particular forecast from Garcon? Well, we've developed a method to do this. And this is a new method which we've been working on over the last year or so, and it comprises essentially 3 steps. So the first step is to create what we call a hydrology tercile lookup table, and we do that using historical drip simulations. So this is illustrated in the figure on the screen. So we run drip with observations, driven by observations, and we generate output for, in our case, we generate 35 years of historical data. We then take that output and we categorize each season according to the total seasonal rainfall in the basin. So for instance, we identify all of the years which had upper tercile rainfall, and we put them in one row, in the top row seen here. And we take all the years with middle tercile rainfall and we put them in the middle row. And then all the years with lower tercile rainfall, they'll go in the lower row. And just as an example, I'm showing stream flow here. It's where the thick blue lines indicate high levels of stream flow. And you can see wetter years tend to have higher levels of stream flow and drier years have lower levels, but there's still variability within each basin, within each category. So if the rainfall is in the lower tercile, there's still quite a high difference in the potential hydrological outcomes. But that is our hydrology tercile lookup table. Once we have that, we move on to step 2, and we can then apply a single tercile forecast, e.g., for example, from the Garcon. We can apply that to our tercile lookup table to create a new water forecast ensemble. And we do that by resampling from each category. We resample a number of members based on the probabilities of each tercile category. So for instance, in a case with the upper tercile probability is 50% and the other 2 probabilities are 25% each, we take 50 members from the top row, 25 members from the middle row and 25 members from the bottom row. Obviously, that's more members than there are in each row, but we do what is called resampling with replacement. So in our resultant ensemble, half of the members are outcomes which could occur with an upper tercile year, and 25% from a middle tercile and 25% from a lower tercile. So now we've got an ensemble. We've got a water forecast ensemble which is consistent with Garcon probabilities and is faithful to those key dryland processes. And now we've got an ensemble, and we can use that to proceed to step 3, which is to create water forecasts. We can then calculate probabilities of any kind of hydrological event based on variables which are only limited by what we can take from drip, and drip simulates the whole range of hydrological processes. So we can look at soil moisture, we can look at potential groundwater recharge, we can look at WRSI, evapotranspiration, and we have stream flow in there, and we have daily and sub-daily stream flow. So we can even look at flood risk variables. In this case, I'm going to show you some things on seasonal metrics, but seasonal metrics where we're counting the number of days in the season which have extreme flow. Now, I'd be very happy to go into the details, more details of this, and any analysis we've done on it, but I'll leave it there for this presentation, and just say that we are preparing a paper which will describe all of the methodology as well as the verification we've done on hindcasts of it. And just to say that verification is indicating that the probabilities this method generates are reliable, and the skill of the output is entirely consistent with the skill of the tercile seasonal total rainfall input. So we're happy that the method is doing what we think it is, and that it's producing reliable information. Now, that's the method, and now we've used it to create some experimental water forecasts for the upcoming season. We've just had the Garcon forecast, and we've used those tercile probabilities to run through our method and generate outcomes and new forecasts for a range of different variables, and we'd like to present those here. So let's look at the Garcon forecast again. So we have Upper Uaso Nyiro here in Kenya, and that's falling in zone 1, this large green area. And here it's indicating 50% upper tercile, 25% middle, and 25% lower. So it's hedging slightly towards wet conditions, and wet conditions. So half chance it will be in the upper tercile. So we run that through our model, and we get outcomes for, in the middle is soil moisture. We have an ensemble of potential soil moisture, seasonal averages. And with that ensemble, we create probability, and we can look at the probability that the soil moisture will be above normal. Now here we're defining above normal in the same way as the rainfall. So above normal is the upper tercile of the soil moisture distribution based on the historical simulations. So the forecast is what is shown in the middle here, where purple colors indicate increased risk, increased chance of above normal soil moisture, and then gray colors indicate the chances between 30 and 35%, which is the long-term frequency of the event. So gray means no increased risk of above normal soil moisture. So the chance is normal. As you might expect, the forecast is consistent with the rainfall. There's more rainfall, so in general there'll be more soil moisture. But we've got more details here. The pixels you see are 1 kilometer resolution. So this is the output in which we're running drip, and this is providing clear spatial signatures and differences between the basin. So for instance, in this case, so just to orientate you with the basin, in the south and southeast is mountainous. So Mount Kenya is around this region. if you can see my pointer, in the southeast. And then the main Iwaso-Nyiro River flows northwards and then turns eastwards, exiting the basin in the northeast here. So most of the basin in the north part is lower land, and then in the south and southeast is higher land, it's uplands. And we see in those uplands, actually there's, even despite there being increased risk of upper tertile rainfall, the chance of upper tertile soil moisture is not changed significantly from normal. So the processes governing the partitioning there are working to somehow to dampen that signal of rainfall, and are not leading to particularly high soil moisture signal. Whereas in the lowlands, the rainfall signal is passing through entirely, and we're seeing enhanced chance of above normal soil moisture. We see, if you look at the top right now, that's a plot for WRSI, which is showing a similar pattern, even a slightly larger region where the rainfall signal has been dampened. And in the bottom right is a plot for potential groundwater recharge, where we see that rainfall signal has been damped even further. We see that the above normal recharge has increased in risk in the northern parts, and actually in the mountainous parts, the recharge is likely to be above normal. But in a large part of the lowlands, despite there being 50% chance of upper normal tertile rainfall, our experimental forecasts suggests this isn't going to translate into above normal recharge. Now, why might that be? Well, we have high evapotranspiration there, and recharge is sensitive to the intensity of rainfall, these short-lived, spatially restricted rainstorms. So even though the seasonal average might be high, if you don't get those high intensity rainstorms, that's not going to translate into recharge. And in a lot of those regions, most years don't have recharge in our simulations. So what we're seeing here is the sort of added value of the embedded information within DRIP, within representing these processes, which can tell us a bit more about what's going on with the hydrology compared to just a basin average tertile seasonal rainfall. We can look at evapotranspiration as well. Shows a similar picture. With more moisture, is likely to be more evapotranspiration. And then look at extreme flow. So in the plot in the right is the probability that there will be an unusually high number of extreme flow days. So we're defining extreme flow by the 99th percentile of the flood duration curve, and we're looking at counting the number of days in season which are above that threshold. And this shows, in general, higher chance of higher flood risk, but the spatial pattern is different. Here in the east of the basin, we see the largest increases in flood risk, but in some parts that increase in rainfall isn't translating so much into increased flood risk. Now, up to that point, what I've shown you is forecasts for what we call tertile events. So what that means is that we're looking at each pixel separately and considering the historical distribution, what is above normal or what is below normal. We look at the years and we take the top third and we call them upper tertile, and the bottom third are lower tertile. So above normal is defined separately for each pixel. So in a dry region, above normal soil moisture it may be quite much lower than above normal soil moisture in a wet region. And that's one way of presenting the forecast by you're essentially taking out that spatial differences in the normal range of hydrological variability. But with our ensemble, we don't necessarily have to do that. We could take what we call physical thresholds. So we could look in our ensemble and ask, instead of is the recharge above or below normal for that pixel? We could say, is the recharge more than 0 millimeters? I.e., is there likely to be any recharge? And that's what I'm showing you here on the screen now on this left plot, which is the probability that given this Garcon forecast, what's the probability that each pixel will see any recharge? And now we have a huge variation in probabilities, ranging from these above 90% in the southeast, where some recharge is almost guaranteed, and these red colors showing below 20 and even below 10% in the gray for most of the region, which is showing that there's, even though the chance of above normal is 50%, there's a very little chance of experiencing any recharge in those regions. And what that's reflecting is two things. One is the probabilities in the Garcon, but the other is the normal frequency of that kind of event at each pixel. So it's synthesizing those two sources of information to provide a probability of that physically defined event for each pixel. So in the southeast, for instance, every year normally has some recharge. So the probabilities of seeing recharge there are quite high anyway. And in the lowlands, the probabilities are lower in most years. There's not much chance of recharge in most years, but it does happen. So we're synthesizing that normal spatial variability with the particular forecast issued from Garcon. And on the right, we see the same kind of thing for looking at extreme flow. So we're asking, what's the probability that this season will have at least one extreme high flow day? So at least one day above the 99th percentile. And again, we see a huge difference in probabilities. Parts of in the south and coming up to the mainstream are showing very high chance, above 80%, above 90%, that there will be at least one flooding day. But in other regions, the probabilities are lower, still above 40%, above 50% in the east. And then there's parts of the stream where our experimental forecast is saying that even though the probability of upper tercile is 50%, there's still less than 20% chance of at least one extreme high flow day. We're not saying the chance is 0, but it's reflecting that spatial difference in the normal occurrence of extreme flow. So those are just some examples, and I'm happy to chat about that. But what we've got now is a chance for you guys to give some feedback on this. I mean, we're really keen to get your opinions on this, because we've been working with ICPAC to kind of develop this and make some prototypes, because these are really prototypes. These are not meant to be in any sense a finished product. What we want is to work together with the wider community to co-design information which will be of most use. So we are so keen to get your feedback, and so we've designed a few more mentee questions to give you a chance to respond, which we'll go to now, and we'll have a chance to we'll talk about the responses and have a chance to add more questions in the chat. So if you've got other questions, then please put them in the chat now, and if even put up your hand if you wanted to have an intervention. So let's go to Mentimeter. If you open up your Mentee app again, and go forward. Right. So the first question is, would you use this type of water forecast in your work going forward? Yes, no, or don't know.
In case anybody hasn't seen, I have put the direct link in the chat box, so you can just click that link and it will take you directly to the question.
So we have some promising answers so far. Six are yes and 3 don't know. Currently no no's. Okay.
Just to say, while people are still voting, that you know, I did mention at the beginning that our aspiration is to have a regional model to cover the whole of that Horn of Africa drylands. So it would be all of these variables that we're describing here would be resolved for that whole region on a gridded basis. But we are actually right now working toward an intermediate step where we might have 3 different basins, one in Ethiopia, one in Somaliland, and one in Kenya, this one in Kenya, to present at a future GALCOF meeting.
Perhaps I can ask a question which people might be wondering about that. Do you have a timeline for the eventual entire rollout and when we might see it across the entire Greater Horn of Africa region?
It's a good question. I would say sometime in 2023. I don't anticipate that it would happen in this calendar year, but we hope to have our regional model working by the end of this calendar year, but we have a lot of tests and evaluation to do before rolling it out within the framework.
Okay, Dave, do you want me to advance the question, or do you want to stay on this one for a bit longer?
I think we can go to the next one. We had 15 responses, which seemed stable. So we've got another question. So we're just now thinking about what the variables that I've shown you already. Just wanted to get a feel for which of those might be useful, which you could see yourself using in your decision making. So we have soil moisture, stream flow, groundwater recharge, WRSI, actual evapotranspiration.
And if anybody wants to add any comments to that, please either raise your hand or type in the chat box.
I can see there's a question from Tim, which is a thanks, Tim. It's a good question. So he's asking about taking into account initial hydrological conditions. Do we take these into account, and how do we do? So, for example, low soil moisture might have an influence on, at the start of the season, might have an influence on the outcomes in the season. Actually, we're not currently taking that into account. So that initial soil moisture can have a predictable impact on it offers predictability. But in our case, the method isn't flexible to take that into account. I mean, what I would say is that in these regions, soil moisture at the start of each season is normally quite low after the dry season. So in most years, the soil moisture can be quite low, and the balance between the predictability offered by the initial state and the boundary conditions, i.e. the rainfall of the season, is highly weighted in favor of the rainfall. So whilst you can get some predictability from the initial conditions, the majority is coming from the rainfall. And I think it's a question we can definitely delve into, but running the model with an initial state and then forcing it with a seasonal forecast, that poses a huge number of technical challenges and philosophical ones as well, which maybe we can leave for another time. But that kind of thing we'll talk about in the paper. And
Dave, there's also a question from Mohammed. Mohammed, thanks for your question. So asking about providing the collaboration results for the model outputs using hindcast historical data, for example, stream flow, groundwater level, and soil moisture for the test catchments. So will you be providing those?
Yes. So in in the one paper that I've mentioned, we'll be providing an assessment of the skill of the forecasting method. But in parallel to that, there is also work on actually calibrating the model, so comparing the historical simulations against in situ data, and that's work that Andres has been leading. I mean, Michael, maybe you can comment on any timeline for that, but we will, of course, we will be sharing that in some form.
Yeah, I mean, there's currently a paper in preparation for the Owasso Narrow Basin, so that will be probably submitted within the next couple of months, and it will be through an open access journal, so it will be widely available.
Okay, that's all the questions so far in the chat box. Looks like we're getting fairly even results for the different variables. If anybody has any comments on their choices, please do leave a comment or raise your hand.
Yeah, so that's 16. I just an addendum to the last discussion. We've been mentioning sort of papers and outputs. If you are interested in any of this, please do follow us on Twitter or keep it up to date with the website. So anything that we will be producing, we'll be sharing through those channels. Let's move on to the next question. So what we want to know now is, are there any other variables related to water which might be useful to be included? So is there anything that we've overlooked?
Yeah, I think this is an open-ended one, so please just type your response and it should appear.
One thing to point out here is that the model is a full water balance model, so it actually can calculate a wide range of variables potentially that are related to the water balance. So that's kind of the way to think about this question, perhaps.
So root zone soil moisture. Can you make any comment on that, Dave or Michael?
Yes, well, it all depends on the root zone, you know, what the land cover is and how that maps to the particular local soil moisture. But that is something we can explore about making sure that we're resolving the relevant root zone soil moisture in different parts of the HAD region.
Okay, we have a couple of questions in the chat box. Any links to be shared to access you for further engagement? We wanted to be able to collect email addresses, but we didn't have ethical approval in place to do that for this session, unfortunately. But I suppose the best way, Michael, sign up for the newsletter, do you think?
Yeah, so I'm going to put an email address for our project here in the chat, and people can contact us that way or through the website.
Okay, thanks, Michael. A question from Richard. Can reservoir inflow be readily derived by integrating over tributaries?
That's a great question. Thanks, Richard. I think so. I mean, we have stream flow across at daily resolution, and if we had a shapefile definition of those tributaries, it should be quite simple to integrate. I think that could be done. So we're running the model currently, as you can see, on a sort of per basin level. So in theory, we could define the basin to be the tributary to a particular reservoir, and it could be run in a bespoke way for particular reservoirs.
Yeah, I mean, if we had some, like Dave said, if we had a shapefile that identified the locations of relevant reservoirs, then I think it'd be straightforward to calculate the cumulative stream flow over some time period that we expect to be delivered to that reservoir.
Okay, another question.
Wait, sorry, Jake. Mark, because he's leading the model development team, he may want to comment further on that point.
Yeah, I was just going to say, I think when we go to the regionalization, the anticipation is that we would include large water bodies in the model. So we'd certainly be able to actually get inflows and outflows of those. So I was wondering whether Richard was talking about existing reservoirs. I guess it's a different question for then thinking about new ways of capturing water in the landscape, which would be a sort of different problem. But hopefully when we go to larger scales, we will have something in there on ponded water more explicitly.
Thanks, Mark. Another question is from Iqbal. What about groundwater potential results? Will you compare with actual water level?
Yes, I mean, I believe in the calibration and where the groundwater observations are available, we'll be doing, we've done comparisons against those.
Yeah, the real problem with groundwater, as you probably know for this region, is there are very, very few observational wells. So it's very challenging for us to make those kind of comparisons. But we're doing the best we can with the available data, and we're even exploring the use of other data sources, such as the GRACE satellite product, to assess our model and to evaluate it. Mark maybe wants to say something more.
Yeah, that's a really good question. It is really difficult to model the groundwater levels. And I think what the approach we're taking at the moment is to think about the groundwater recharge. So in that sense, it might give people a sense of whether there's likely to be a recovery in levels during, because of rainfall, which I think is an important thing for, the access to water from individual wells, for example. But the actual, we're not going to be able to resolve sort of well point resolution in this model. So we have to be very careful about what we report. But it's something we're thinking very hard about. Yeah.
Okay, we've had some more responses on the Mentimeter question. Perhaps Dave and Michael can comment on the feasibility of some of the suggestions.
I mean, certainly runoff we have that's defined for every pixel, not just the stream flow. Root zone, soil moisture we've covered. Soil temperature.
I don't think that one is realistically possible under this modeling framework. There's too many unconstrained variables there that, but feel free to correct me, Mark or Andres, if I'm over speaking here.
So yeah, so the model is our primary aim is the partitioning of water, and so with temperature, factors like cloud cover and radiation and surface energy exchanges might make things, well, in its current form, I'm not sure if it's possible, but water level and water coverage, certainly. So we have runoff, and I mean, maybe one of the developers could comment on this.
Actually, can I just say a brief word, because inundation is listed there as well, and this is a conversation we've been having with FAO Swalim as well, because there is a lot of interest in understanding potential areas of inundation during flood events. So one possibility is that we would take our model results and connect them to a flood inundation model to explore the spatial coverage of inundation. But this is just in its early stages of conversation rather than something that we're promising in the short term.
Yeah. At Bristol, there is expertise in modeling this, and we are currently working on separate projects looking at producing inundation mapping across East Africa, including Kenya. So that there's certainly potential there, but as Michael said, there's nothing concrete promised yet. I think we've maybe had enough time this question.
Yeah.
And we have a final question, which is wanting to know what would you need to help you use this forecast? So are there any barriers which would prevent you from using this information? And is there anything that could help facilitate the understanding or the use of the information? And that could be from our side. Could we present it or provide it or process it differently? Or it could be from your side. Are there things that you might need in order to use it?
Feel free to use the chat box or raise your hand if you'd rather, instead of mentee. So we did have one comment in the chat box about earlier, I think, about training. Let me find it.
More documentation. Yeah, sure. I mean, so in terms of documentation, there's already the paper out for the model itself. There will be a paper forthcoming about the forecast production methodology. And as the development of the quality system grows, we'll be looking to publish open access all of the key parts of that system. But certainly it would be great to get feedback on the parts which are in need of documentation. If it turns out there's parts which are more tricky to understand, we can certainly work towards improving documentation on that.
The other thing to say, maybe I'm preempting what you're going to say, Jake, is that we do plan to embed this modeling system within ICPAC's workflow, and associated with that, do a whole load of training workshops for different potential users across the EGAD region. So I think there will be opportunities in the future to engage further with this and learn more about it. And just to address, related to that, Richard asked whether this model might also be applied outside of the ASAL regions. And I think, yes, I mean, this model, it works in dryland regions, which you can say that many models don't work in dryland regions, but it also would work in a humid region because it allows for the groundwater surface water interactions to generate perennial flow within channels. So simply allowing the water table to come up to the surface and that base flow to be driving stream flow, in drier periods is something that's innate to the model.
See, we've had someone else is interested in training as well. I think that's a critical part of this. I mean, so just to add to those comments, we could train on the use of the model and also on the generation of forecasts, because we have, in this example, we're showing the integration of the modeling system with the Garcon terrestrial probabilities, but in theory, it could be used with other probabilities. If there was an alternative forecast or an updated forecast as the season progresses, that could be easily used with the method. And yeah, certainly training could be provided on how to do that.
Yeah, we had one comment about just capacity building, so I'm guessing that covers training in general, etc. But that seems to be everything.
Great. Well, thanks everyone for all your responses there, and do feel free to add more in the chat if anything comes up while we move on with the presentation. That's really helpful and really great to find out what you're thinking. Now let me switch back to our, that's the end of the mentee. Switch back to our, at this stage, we were going to do a live demonstration of all of this information on the East Africa Hazards Watch. And now I will do a final check to see if it's working, but as of the start of this presentation, it was not working. So let's just, it does seem to be hanging, but I will put the, so this is a demo version of the Hazards Watch. This is not the live public version, but this is just to represent the fact that these are experimental forecasts and it's not been fully integrated. I will put the link in the chat, so at some point you can have a look, and hopefully once it's all back together, you can play around with these layers. But instead, I've got some slides, screenshots of what's on there, so hopefully it can give you an idea of how to access it and what we've provided. So if you navigate to this link, to that URL, you'll find the East Africa Hazards Watch. For those of you that are not familiar, this is providing a whole bunch of layers of different variables, from forecast to historical data to impact data, to be a one-stop shop for all kinds of contexts, to provide the context of risk of climate and climate impacts over the region. So we've got rainfall, temperature, climate change, agriculture, etc. Now, if you look down on the left panel, you will find a new layer called what we're calling water security for now. And if you click on that, you'll see a whole bunch of different checkboxes for different variables here. And if you choose one, then we'll zoom into our test basin and you'll see the forecast. In this case, it's showing potential groundwater recharge forecast, the physical probability. And then there's one choice of physical threshold, which is greater than 0 mil recharge. And you can see the probabilities on the map. Now, I'll run through what we put on there. So we have our initial focus of the 5 variables you've seen already: soil moisture, extreme stream flow, potential groundwater recharge, actual evapotranspiration, and WRSI. And for each of those, we've got 3 kinds of layer. We've got a historical layer, which is providing the historical simulations from DRIP. And then we've got tersoil probability layer, which we've been showing already. So this is providing the forecast for MAM 2022. And we've also currently got on there forecast for a few historical forecasts, so for OND 2021 and for MAM 2021 as well. And as well as the tersoil probabilities, there's a physical probability layer, which is representing the physical probability forecasts, which we discussed already. So let's have a look at each of those in turn. Firstly, the historical data. Here's an example. If you go navigated down to potential groundwater recharge and then selected the historical layer, it pops up with a map of which represents the historical simulation for MAM groundwater recharge. Here it's showing MAM in 2016. So this is units of millimeters, and it's showing you where groundwater recharge was higher or lower. And this showing you in the southeast of the basin, Mount Kenya, there's very high recharge along this border. And actually in the southwest as well, and in the north, there's some substantial recharge. For most of the basin in this particular season, there was less than 1 millimeter recharge. And now you can choose another year. Let's click on year and select 2015 to compare. So 2015, and then we see a different picture. See slightly enhanced recharge in a different region, and and no recharge in the southwest. And we can choose another year, 2014. This was a particularly dry year in this region. And here, less than 1 millimeter recharge across the whole basin. with very restricted areas of recharge right in the south and Mount Kenya. And you can look at any year. We have, at the minute, we have simulations from 1983 and they finish in 2016. But we will be extending that to the present day. It's not just MAM. We have all possible 3-month seasons. So you could click on, well, let's look at a big example. So let's look at OND 1997. So you may well be aware that OND 1997 was a very large El Nino event, with a very large Indian Ocean dipole event, and it was very wet. And this, we can click on season OND year 97 to find out what the recharge looked like for that year. And we see, as we might expect, huge recharge, a lot of high intensity rainfall events in season, a lot of recharge. But we see it's not a homogeneous pattern. We see areas where the recharge was still quite low in the northwest of the basin, despite the heavy rainfall. There's areas where there's still less than 25 mil of recharge. So you can, it's really, I mean, I think it's really cool to just play around with this and explore. And you see these huge spatial gradients in recharge. So that's all historical data. And we've got those, that kind of information for all of the variables you see. So you could go and explore the historical WRSI or the extreme streamflow or whatever you like. And you can overlay things. So you can compare and contrast different variables or different years. Beyond the historical data, we have terrestrial probabilities. So these are what we've seen before, just show that so if you click on the terrestrial probability for soil moisture, you see, I'll just note this forecast is from 2021 because from MAM, this was before we had the live forecast. So this is not the current forecast, but the current forecast is on there once you can get to it. But here now we can click through above normal probabilities or near normal or below normal. So in the side here, and you could select a different forecast for different year and different season. There's a few on there, as I said. And here we see the probabilities of above normal soil moisture, similar to the current forecast, where the probabilities are dampened in the mountainous region, and probability of below normal here. And finally, we have the physical probabilities. What I'm showing here is the probability for extreme streamflow. So this is okay. So this is not updated, but what we would be showing for extreme streamflow is the probability of at least 1 day of flow above the 99th percentile. And we're showing that from 10% through to 90%, because as we've discussed, those kind of probabilities are much wider in range compared to the terciles. And so for this table here, if you focus on the table, you can see that we've got each of our 5 variables on each of the rows. And for each of those, we've come up with some illustrative physical probability just to start with. So to try and capture some kind of physical event which might be meaningful or worthwhile trying to forecast. So for soil moisture, we're looking at what we're calling severe plant stress, which is 25% between wilting point and saturation. Extreme streamflow, at least 1 day above the 99th percentile. Groundwater recharge, looking at more than 0 millimeters. And evapotranspiration above 250 mil and WRSI below 0.5 mil. But those thresholds, as I've said, those are just sort of placeholders to say this is the kind of thing we could do, and those exact thresholds we might use are where we could really we would really benefit from expert insight and use anyone who potential user insight. What thresholds might be useful for you? Are those thresholds useful? And that if you've got any thoughts initially, please do chuck them in the chat, or we'll have some feedback in a second. but that's an ongoing process. So it would be great to stay in touch, and if you want to be part of the sort of development of these, you're very, very welcome. Just get in touch with us, and we'll work together going forward. That's all I had for these. That's where I'll stop with the demonstration. I was going to take suggestions to click on more things for the layer now, but we're not live, so we'll leave it there, and hopefully the link will work at some point if you save that URL. And then I'll throw it back to Michael then to finish us off with an outlook, and then we've got time for some live discussion.
Yeah, thanks, Dave. I hope this was informative and helpful for many of you. I mean, we do want to solicit feedback and opinions on everything we've done here and shown to you. So don't hesitate to get in touch. You can see the various ways to contact us on this slide. And you know, we're building our stakeholder group and trying to grow it, and to get the information out to that broader group about our project. So please let us know if you want to be included in our mailings, but also if you'd like to participate in any future focus groups, which are much more targeted toward getting specific types of outcomes in a research way. But I want to give enough time for people to ask open-ended questions about anything that we presented here or anything related to it, including questions about the model, about modeling in general, and about the sorts of outputs and the forecasts that we've generated here. I think at this point, we can just open the floor and maybe switch off the screen sharing and allow people to engage a bit more.